This is Ruby. Today we're going to talk about hypothesis testing one-tail. So, the college is interested in whether providing a student-parent program leads to higher grades. To evaluate the effectiveness of the student-parent program, a random sample of 36 students are placed into the student-parent program. The average final score for the student-parent program is going to be measured, and it comes out to be a sample mean of 76. For the general population, the average sample is mu of 72. The population standard deviation is 12, and we are going to do a one-tail test for alpha equals 0.05. All right, so the first thing we're going to do is we're going to identify the hypotheses. So the first hypothesis would be that the null hypothesis is that the mu of the program, which was equal to 72, is that it has no effects on grades. So it would be equal, or it could even have a negative effect, so it would be less than 72. The alternative hypothesis, which is the H1, is that what the researcher is hoping to find is that the program, the student-parent program, will actually reflect in higher overall exam scores. So they're hoping that the mu of program will be greater than 72. And please recall that whenever we do hypothesis testing, the mu's are always going to be around the population. And also please recall, for a one-tail test, you either use combination of greater than and less than or equal to, or you use a combination of less than and greater than or equal to. So those are your only two choices whenever you're writing out those hypotheses. Now, for the second step, what you're going to do is you're going to identify the critical Z and the statistical significance region. You're going to use the following information. In this particular case, you have one tail, so it's only going to be one region, and alpha equals 0.05. And please recall that since you have only one tail, and we're expecting that it's going to be greater than our population mean, it's going to be in the positive direction. So when we look in the Z table, we're going to be looking for 0.05 as the proportion that's in the tail column, and then we're going to find the Z that corresponds with that 0.05 that's in the tail. All right, so we go ahead and we go to our Z table, and remember, proportion in the tail is in the Z column, C as in canary, and we're going to look for the Z score. So what we find is that there's two choices. We have a proportion of 0.0505, which is a bit over 0.05, and that is associated with a Z value of 1.64. The other possibility is a Z of 1.65, which is associated with a proportion of 0.0495. That's the one we're going to use. It's a little bit of a conservative estimate, and we don't want to capitalize on chance, so we're going to use the Z of 1.65. So what you know is a Z of 1.65 would then be equal to 0.05 proportion in the tail. So we're going to go back here. We're going to make our drawing, and what we found was that the Z value was equal to 1.65, and it can only be in the positive tail. So we have 1.65 in the positive tail, and we know that anything that falls above 1.65 would be statistically significant. Now again, this is our Z critical, and we have to think about this because let's say we found a Z and it was negative, and it was negative 3.25. Well, certainly that would be in the tail, but that is in the wrong tail, so it will not be significant. It has to be in the right tail. So in this particular case, the correct tail would be on the right-hand side, which is a Z of 1.65. The third step now is to do our computed Z, and that's what we're going to compare to that critical Z of 1.65. So we do our equation of Z equals the sample mean minus the population mean over the standard error, and the standard error equals, as you will recall, the population standard deviation over the square root of the sample size. So we have 12 over 36 in this case, and those are values that were given to you at the beginning of the problem. And so 12 stays as 12, the square root of 36 is 6, and so 12 divided by 6 equals 2. And then we go ahead and figure out our Z computed. Well, that is merely taking, again, the sample mean minus the population mean and divided it by the standard error. So we have 76 minus 72 divided by 2. So 76 minus 72 equals 4. Divided by 2 would be 2. So our z computed would be 2. So if we look back at our drawing, what we see clearly is that z of 2 would fall into our statistical significant area. So if it falls into our statistical significant area, then we know that indeed we have statistical significance in this case. All right, so the final couple of steps are we have our z computed, which is 2.0, which is greater than our z critical of 1.65, so there is statistical significance. So our conclusion would be that we would reject our null hypothesis. So we found evidence that indeed our students are doing better than the general population in terms of their final exam scores. And we found that we accept the alternative hypothesis because they are doing better. So remember that the null hypothesis said that they would do worse or equal, and we found that that was false because they're actually doing better. So we reject, which means that the null hypothesis was false, and we accept the alternative. And then finally, to describe this in words, we found that the grades of the students who participated in the student parent program showed a statistically significant improvement in grades over those students who did not participate in the program. So that would be your final statement in words. And then the last part would be Cohen's d. Now remember, we talked about Cohen's d, that it can be manipulated by sample size. So we take sample size out, and we have a lowercase d equals, we have the sample mean minus the population divided by the standard deviation. So we have 76 minus 72 divided by 12, and that gives us 4 divided by 12, which equals 0.33. So this is also a small effect. And that's all for today. And we'll talk soon. Bye.